दोस्तों, वेलकम टू द क्लास। हम सॉल्व कर रहे थे प्रॉब्लम्स ऑन साइक्रोमेट्रिक प्रोसेसेस। So this is our fourth problem. The following data are given for the space to be air conditioned. Outside air design condition 40 degrees Celsius drivable temperature and 50% RH. Inside design condition 26 degrees Celsius drivable temperature and 50% RH. Apparatus dew point temperature, that is coil temperature, 10 degrees Celsius, and bypass factor of the cooling coil is 0.2. The return air from the room is mixed with the outside air before entry to the cooling coil in the ratio 3:1 by mass. If 20 meter cube per minute of fresh air is supplied, find condition of air leaving the coil, capacity of coil in turn of refrigeration, and sensible heat factor. Now, if you read the problem carefully, you will get the how the air is flowing. So I will draw one sketch so that you can understand very well how the air is flowing. For example, let us say we have this room which is to be maintained at given condition, that is inside design condition, at 26 degrees Celsius travel temperature and 50% RH. So this is what inside design condition we can write, or we can say room inside condition, right? So in order to maintain this inside condition at 26 degrees Celsius travel temperature and 50% RH, we are supplying some heat air from this side. Okay, and before this the air is passed over the coil. So this is called as the coil. It is a cooling coil, right? Now they are saying that some amount of air is fresh air which is passed on the coil, and some amount of inside air is again recirculated. So I can take the flow like this. Okay, so some amount of air is mixed with this like this, right? So fresh air, we can write that for that fresh air as O, and return air, that is inside design condition, the return air is having inside design condition, so that is indicated by I. Okay, so both two airs are mixing together, so mixture point is indicated by M point. Okay, which pass on this coil. After the coil, whatever the air condition is, that is nothing but supply condition, so we denote it by supply condition S. Okay, which is responsible for absorbing heat inside the room. Okay, so this is what actually the situation is. So let us first of all write what is given in the problem. Outside air condition is given, so we can write outside air condition, outside condition so drivable temperature is given TDO, which is equal to 40 degrees Celsius, and relative humidity is also given, so RHO, which is equal to 50%. Along with that, inside condition is also given. Inside condition, travel temperature here is 26 degrees Celsius, and RHI is again 50%. Okay, so first of all, what we do, we plot these 2 points on the psychrometric chart, specifying outside condition and inside condition. So this is our psychrometric chart. So our outside condition is 40 degrees Celsius and 50% RH. So if I follow this line, of 40 degrees Celsius upward, right, and we have 50% RH, so this point, that outside condition point, would be over here. Okay, similarly our inside condition is at 26 degrees Celsius, so this is my 26 degrees Celsius line. If I follow this vertically, I have 50% RH also, so this is what the 50% RH line. So those two will coincide at this point, so this is what our inside condition. Okay, so if I draw this, is how I get the point O and point R. R indicates the room condition, okay, or we can denote it by I also, okay. Now these two streams O and R are coming together forming mixture, okay. So that condition of the mixture will be on the line joining this R and O, okay. So that is what my line is. So on this line I will get the mixture point, so it is indicated by M point. So let us first of all find out that condition which is given in the problem. Now we have given that fresh air added, how much it is? 20 meter cube per minute. So that is what the fresh air entered into the system, okay. So fresh air added is given 20 meter cube per minute. Along with this one, we have given the mass of return air divided by mass of outside air. So that is ratio is given to us, okay. How much amount of mass of return air is there, that is fresh air, and return air is there, right? So that ratio is given to us. So we can write that as mass of return air and mass of fresh air. We can write fresh air, that is equal to 3:1 given to us. So let us first of all find out what is mass of fresh air and what is mass of return air. That we can get from the data given, right? So let us first of all find out mass of fresh air. So I will indicate by it by m dot o, right? How to calculate that? It is equal to volume flow rate of outside air, that is fresh air, divided by VSO, that is specific volume at O point in the psychrometric chart, okay. Now corresponding to that O point, if I try to find a specific volume corresponding to O point, it comes out to be equal to 0.922, because this 0.90 is there, and if I divide this section from this line to this line in 5 parts, I will get the volume corresponding to this O point near about 0.922, okay. Similarly, point R, we will get some specific volume, okay. So this is how we can find this specific volume. If I put the value in this VO, that is equal to 20, and VSO is given as 0.922. So if I try to solve this, I'll get answer as 21.7 kg per minute, okay. Outside air mass flow rate, that is fresh air mass flow rate, that means over here, right? So this fresh air is added with rate of 21.7 kg per minute, right? Now we will take help of this equation now to find out the mass of return air. So that is equal to how much? M dot I. We can write M dot I. So that would be equal to, from this equation we can say it is equal to 3 into mass of fresh air, right? So that is M dot O. That would be equal to 3 into 21.7. So if I try to find out this answer, so I'll get that answer as 65.1 kg per minute. Now we got the mass flow rate of O also, that is fresh air, and mass flow rate of return air also. So both two streams are mixing together and forming this M point, okay. Now here we have to find out the mixing condition, that is the dryable temperature of mixing air, right? So that can be written as Tm. I'll indicate that by Tm. So that would be equal to how much? M dot O into TO plus M dot I into Ti upon M dot O plus M dot I. Okay. So this would be equal to M dot O. How much it is? 21.7. So it is 21.7 multiplied by TO. outside condition, how much it is? 40 degrees Celsius, plus m dot I value is 65.1 multiplied by Ti, how much it is? 26 degrees Celsius. So divided by total volume flow, total mass flow rate, that is 21.7 plus 65. So if I try to solve this, I will get Tm, that is mixed air temperature. So that is equal to how much? 29.5. Okay, that is equal to 29.5 degrees Celsius. So this point, if I try to plot on the psychrometric chart, that would be on the line joining this R and O point, where 29.5. So this is what my 30-degree line, and we have here 29.5 line. So if I go vertically upward, so I'll get the point simply over here. Okay, so that is how it is M point. Now ये जो air है at M point, so on the flow diagram it is at this full position. So when that M air, mixed air, pass on the coil, the cooling takes place. So whatever the air that comes out from this coil is, we get that point at S point. So this S condition, the condition of the air outside the coil, S, depends on the bypass factor of the coil. Okay, so before that we will go on the saturation line. So we plot the ADP, that is apparatus dew point, on the psychrometric chart. So on the saturation line, this is, so apparatus dew point temperature given in the problem, it is 10 degrees Celsius. So the point that we plot on the psychrometric chart corresponding to 10 degrees Celsius is this one. That is called as apparatus dew point temperature. Now the condition of the air, that is S condition, outside the coil will be on the line joining this ADP point and M point. Okay, ADP point and M point, and that point exactly where it depends on the bypass factor of the coil. If the bypass factor is 0, then the ADP is nothing but the outside condition. If the bypass factor is 0, then ADP is nothing but the outside condition, that is S condition. But since in this problem bypass factor is given, that point, that is S point, will be on the line joining this ADP and M somewhere. Okay, so that condition we have to find out. So let us go for the bypass factor. So we have here bypass factor. The formula for the bypass factor we have is equal to, we can find it using the sketch also, right? So if I say this is the coil temperature, this is coil temperature, and my air is cooling from this side to this side. Okay, from this side to this side, right? Which has the air at the entry M, that is Tm. So it comes out from the coil and we get the temperature just above the coil temperature. That is because of the bypass factor. So here also we have Tc. What is bypass factor now? The difference between coil temperature and supply condition divided by difference between coil temperature and mixed condition. Okay, so that is how it is. So I will write that as Ts minus Tc divided by Tm minus Tc. That Tc is nothing but apparatus dew point temperature. Okay, so if I put the values here in the problem, bypass factor is given as 0.2, so 0.2 there, equal to Ts, that is nothing but the supply condition that we have to find out, and coil temperature is 10 degrees Celsius, so 10 divided by mixed temperature, how much? 29.5. 29.5 minus 10. Now if I try to solve this one, I will get the condition of supply air as 13.9. Okay, 13.9. Now this point, if I try to plot on the psychrometric chart, I'll get that point on the line joining ADP and M. So how much it is? 39.9. This is 10, 11, 12, 13 and this is here 14. So near to that line we have this point somewhere here. Okay, that is how it is. So that is nothing but the supply condition. Okay, so corresponding to these supply conditions we have to find out all the properties which we are which in the problem we have been asked, right? So the travel temperature we got corresponding to S point, that is 13.9. So wet bulb temperature corresponding to this S point we can find by taking this point on this line, on the saturation line, following constant enthalpy line, and the value somewhat here, the wet bulb temperature corresponding to this point would be equal to how much? 12.9. So this is 12, and this point is not on directly on 13, but it just before that. That's why we take that as 12.9. So wet bulb temperature is how much? 12.9. So supply condition. Supply condition. So that is equal to how much? TS, that is T variable temperature of supply condition, 13.9 degrees Celsius, and wet bulb temperature of supply air is equal to 12.9 degrees Celsius. Now next we have to find out the capacity of the coil. Okay, next we have to find out capacity of coil. Capacity of coil. What is the capacity of the coil? It is nothing but how much amount of heat that is absorbed by the coil from the mixed air. Okay, so that is nothing but what? That would be equal to total mixed air mass flow rate multiplied by enthalpy difference. Okay, so it is equal to HM minus HS. So if I explain this, so this is how my coil is. This is my M air and this is S air, right? So the M air is at high temperature and S air is at low temperature, meaning that the coil which absorbs some amount of heat from the mixed air. So that absorption is equal to enthalpy difference from this M air and S air. So that is how it is multiplied by total flow rate of the air. Okay. Now how to find out this HM and HS, that is enthalpy at M point and enthalpy at S point. So that for that purpose we have to go on the psychrometric chart. Okay, so corresponding to M point, if I follow this line, I'll get enthalpy on this enthalpy scale. Okay, so HM I get corresponding to this line equal to 65. Okay, and the enthalpy corresponding to S point, I'll get that as near about 36.2. Okay, it is 36 point. So from psychrometric chart, we plot this HM which is equal to 65 kilojoule per kg and this HS as 36.2 kilojoule per kg. And what is total mass flow rate? Right, total mass flow rate is equal to sum of M dot O. We have M dot O as, we have solved this in previous slide, that is equal to 21.7 kg per minute, and we have M dot I also, that is equal to 65.1 kg per minute. Okay, and what is M dot M? That is mixed air. So that is would be equal to M dot O plus M dot I. Because if you see here, the fresh air is this one and I air, that is return air, is this one. So this air coming together forming one air. So mass balance हम लोग करेंगे, तो mass of M air is equal to mass of outside air plus mass of inside air. Okay. So if I try to solve this one, I'll get that answer as 21.7 plus 65.1. That would be equal to 86.8 kg per minute. Okay. Now, to find out the capacity of the coil, so we can write now capacity of coil, cooling coil, that would be equal to m dot m. So it is equal to 86.8 multiplied by hm, it is 65, and hs 36. So if I solve this, I'll get answer as 2499.84, that is in kilojoule per minute. Okay, if I try to convert this into kilowatt, we have to divide it by 60. Okay, so this would be equal to 41.664, that is equal to in kilowatt. So this is what the capacity of the cooling furnace. That means what? It can absorb heat of 41.66 per kilowatt. Okay, if I convert this, or if I try to find the capacity of the coil in turn of refrigeration, I have to divide this by 3.5. Okay, so the total capacity I will get in turn of refrigeration as divided by 3.5. So the total capacity I will get as 11.9 TR, turn of refrigeration. Okay, now the last point that I have to find out in this problem is sensible heat factor. Okay, now this is what our supply air is, right? Now this supply air is responsible for absorbing heat from the room. Whatever the total air in the room is, that air is absorbed by this supply condition, right? So that process is indicated by the line joining this S and R. That is called as room sensible heat factor line. Okay, so this line is nothing but room sensible heat factor line. Okay, now if I extend this line SR up to the sensible heat factor scale, so if you notice, this is for the sensible heat factor line, right? Why I am extending this? Because this R condition is nothing but the reference condition, which is 26 degrees Celsius and 50% RH. That's why I can extend this SR line up to the sensible heat factor line. अगर हम लोगों को एक और कंडीशन दिया रहता R का, then I have to take that point, I have to draw a parallel line S to R. From the R point, that is the reference point, I have to draw again a line up to the sensible heat factor line. So that line going to be from the R point parallel to the SR line. Okay, but here in this case, this R is also a room condition and it is also a fresh air condition. That's why we can extend a line SR up to the sensible heat factor line to find out the sensible heat factor. Okay, so that is how it is. Now corresponding to this point on the sensible heat factor line, if I notice, the point is near about 0.78 sensible heat factor. Okay, so the room sensible heat factor from the sensible heat factor scale is found to be 0.78. Okay, so this is how you can solve problem. Thank you.